So on the schedule, the way it was, the way I set it up, oh, it's back. Where is it? No. We can deal with this. Today was sort of a short list of topics with the sort of the introduction to hydrocarbons. And then Monday is the naming, is when we start naming hydrocarbons in earnest. And I fully expect after you look through that, and there's videos on how to name, I fully expect you'll be loaded with questions on Monday about naming, because this is a brand new it's a brand new topic with a whole bunch of different kinds of rules. So we'll start going through naming, and we're going to basically go through those names kind of systematically and name all the different functional groups. So that's kind of where we're going to be. So today was kind of a shorter reading list, but I intended on using the time to answer questions, go over. I can make up problems since I apparently don't have access to the internet problems, but that's okay. I've been doing this a long time. I have more than enough problems I can give, but let's start with questions. Did anybody have any questions, any topics that we would like to review?
Would there be another resonance extension?
Resonance structure?
Like ranking them maybe?
Oh, okay. Sure, we can do that. Let me think of a good one. Let's say we have this structure, and let's work through we can work through the drawing a resonance structure first. Now, I don't know if this is neutral or negative, so why don't I give you a minute to go through here and put together a resonance structure, and if you have an unpaired or an uneven number of electrons, you need to add one to make it a negative charge. If you can put the structure together as is and you end up with an even number of electrons, then you don't need to add one. So I can't remember if this is a -1 ion or if it's neutral. Okay, so I'll give you a couple minutes. Draw a one resonance structure for this. And if you get the first one drawn, then you can go ahead and draw another one. I believe there's 3 total that you can draw. And you can discuss as you're doing this.
This is for Wednesday.
Oh, that's fine. Were you able to see everything online?
Yeah, it's all there.
Okay, no problem. Okay. So let's see. Carbon 6, nitrogen 5, oxygen 6. Sorry, carbon 4, nitrogen 5, oxygen 6 for valence electrons. And it looks to me like we need to add an electron to it so that it is the -1 anion. So there should be three of these resonance structures that you can draw. So if you want to try, so once you get the first one, then you can try and draw the other 2 and rank them. See how far we can make it. So I didn't put the extra electron in here. I'll just put it there. That's kind of a starting point. just pick it up and move it somewhere else. I think you got too many electrons. Yeah, if you start with that, right? So if you start with that, then you can, I think the problem is you have right, so then they add up, so probably that's right. Now you just want to start moving the little pairs of double bonds around to form the other two. There's no hydrogen on the oxygen.
Okay.
So you're starting here. So you're starting with this one. You want to start moving the unpaired electrons and all pairs around. But there's no hydrogens on that oxygen. Remember, as you're writing resonance structures, nitrogen, oxygen, and carbon cannot have 10. So if it has 10 electrons, you need to move those 2 electrons out to some other atom. If there's no other atom to move them out to, you may have 2 electrons too many in your system. Your formal charges have to add up to -1. No hydrogen on the oxygen. You can't move the hydrogens around. The hydrogens have to stay bonded to the carbon. Once you start moving atoms, you would no longer have resonance structures. You have new structures altogether. So no expanded octets, formal charges have to add up to -1.
So would these two have to have radicals since the main one is?
So you can't, there's this structure that I have right now needs to have those 2 unpaired electrons paired up. So once you pair them up, then you can generate the other possibilities.
So these.
I haven't finished this one yet.
2, 4, see that's got 10. So you may not be able to form the structure with the double bond with the 2 double bonds. Right, you just have to make sure you're. Well, right, because I'm going to pair up the end of the O right now. And then once I have that, then I'm going to try and figure out how to.
That one's still compound? One?
Really, so that makes sure. Well, sort of, except the problem is it has unpaired electrons and it has uncompleted octets. So that's going to be two negative things against it. Okay, how many resonance structures have we gotten so far? 2, 3, 2. All right, let's see what we've got then. So for this structure, here's the way. Where's my pen? Here's the way I do it. I don't know. Everybody has their own system, and Lord knows I don't want to mess up any student's system, because I used to have research students, and they would say, "Don't mess up my system. I have my system. Leave it alone. Don't mess it up." And I didn't want to mess it up. So if we have a -1 charge, first of all, I have to give you the core of the structure, how the molecules are bonded. Now it's just been one of those weeks. This structure has as a center atom in the nitrogen probably not the least electronegative structure, so it's going to be a little bit different than other ones. But what I do is I say, okay, let's put in the neutral atoms, the number of electrons for the neutral atoms. So carbon would have 1, 2, 3. It needs an unpaired electron. Nitrogen has 5, so it's got 1, 2, 3, 4, 5. And then the oxygen would have 1, 2, 3, 4, 5, and 6. And so if it's a -1 charge, so that's just neutral. And I know a lot of you count up the total number of electrons and try and fit those around the structure. I always just focus them on the individual atoms so that I don't have to worry. If I have to move things around, I'll move things around. So now I need one more, and where should I put it? I just put it on the carbon. Could you put it on the nitrogen? Yes. Could you put it on the oxygen? Yes. I just like to pair things up. And so now if I'm sitting here with this resonance structure, is this a stable resonance structure? And the answer is no, because it has unpaired electrons, but more importantly, the nitrogen and the oxygen do not have full octets. So then I would go ahead and pair this up. So the first resonance structure I could have looks like this. If I pair up those two unpaired electrons. Now, first thing we check is, do all the atoms have octets and there's no expanded octets? So it passes that. How about formal charges? What would the formal charge on the carbon be? -1. So it owns 1, 2, 3, 4, 5, and it came with 4, so it's a -1. How about nitrogen? 0, and oxygen? 0. So the -1 charge is on the carbon. All right. So this is a perfect time for us to talk about arrows and how to use the arrows to convert one resonance structure into another. So if I want to write the second resonance structure, here's what I need to do. I need to think about how to move a pair of electrons to form a bond. And my choices are, I could move this pair of electrons to the right, or I could move this pair of electrons to the left to form either an NO triple bond or a CN double bond. Let me start with taking the lone pair on the carbon and moving it to the right. So let me grab this, and I'm going to go ahead and use it to form the CN double bond. What's my problem? If I take this lone pair to form a double bond to the nitrogen, then if I stop there, what happens? I get a double bond to a nitrogen with the lone pair and then a double bond to the oxygen with its lone pair. And so what happens to nitrogen? It has too many electrons because it can't form an expanded octet. So if I'm going to make that move of moving this pair of electrons, I'm going to do this. I hate this. This mode on my computer completely screws everything up. But I'm going to go to slideshow mode, because when I go to slideshow mode, then I can point. And then you should see my pointer, which is now a dot instead of an arrow. I don't know why. So if I take my lone pair and I move it here, the only way I can stop nitrogen from having an expanded octet is then to pick up this pair of electrons and now move it to the oxygen. So that way the nitrogen avoids having 10 valence electrons. Okay. And so if I do that, what I'm going to end up with is I'm going to end up with the H attached to the two H's attached to the carbon, double bond to nitrogen, single bond to oxygen with 3 lone pairs on the oxygen. Okay, so this is not allowed because the nitrogen would have an expanded octet. That is not allowed. Okay. So are there any other resonance structures I can legitimately draw here? I could pick this pair of electrons up and I could move it back here, but then I got to move those back there. What does that do? That gets me back to the beginning. So again, an arrow with a full head shows the movement of 2 electrons. And so if I wanted to convert the first resonance structure to the second one and vice versa, then that's how I use my arrows to show the movements of the electrons. And you always have to you always have to try and move the electrons that are at the end of the system. The ones, if there is a kind of a double bond system, you always have to pick the lone pairs that are at the end. Okay. So for this one, there's only 2 resonance structures. Okay. If you were looking at this going, well, wait, isn't this like the one we did the other day where there were 2 double bonds in the middle? Apparently not. Because 2 double bonds to the middle atom violates the octet rule. So you have to kind of take each structure on its own.
What if, like, in the original one, you just moved nitrogen's single electron over to oxygen? So you have, like, all single bonds? Is that possible?
Let's take a look at that. So in other words, lone pair there, and then 3 lone pairs here. Now, so this is a resonance structure. I guess the question would be, is it a stable resonance structure? Because what does this have? What's the knock against this? What's the negative against this structure? The nitrogen doesn't have a full octet. So oftentimes in these problems, what I will do is I will say, make sure that the resonance structures you're drawing all have completed octets to begin with. Because our rule number 1 was that if it didn't have a completed octet, it wasn't going to be stable. Or it certainly wasn't going to be the most stable. So if we get into the issue of having to write resonance structures that don't have completed octets, there can be like 5 or 6 of those. And the problem is they aren't very stable because they don't have completed octets. So while this is a legitimate resonance structure, it's not very stable. And it doesn't fit rule number 1. But we could keep it in there if you wanted to. So if we're going to do that, then we need formal charges. Okay. So we all agreed that these 2, A and B here, are the legitimate resonance structures with completed octets.
Triple bond the N and the O.
Could we triple bond the N and the O? Let's try. Let's try. So let's see. Do you want to do it with? You want to do it with the carbon having lone pairs, right? Okay. So in order to get that, in order to get that triple bond, I'm going to take this pair of electrons and I'm going to give it to the nitrogen to form the N triple bond, the NO triple bond. Okay, so I've got my lone pair there. I've got my N triple bond to O. Is that legitimate? Why not? Because now oxygen has the expanded octet, which it's not allowed to have. So there's no harm in trying. But when you look at it, you go, yeah, no, that's not going to happen because oxygen can't form an expanded octet. So you can try all these different combinations, and that's kind of what you have to do. What the arrows allow, by using the arrows, what it allows you to do is to get one, and then by using the arrows, you can generate the other ones sort of in a systematic way, as opposed to just picking up pairs of electrons or double bonds and starting to try and move them around.
On like a test, do you want us to use the arrows, or if we simply just like draw the 3 different structures?
Probably for the first test, I would just ask you to draw the structures. Unless I said specifically show the arrows, but I might give you another problem to, where the arrows would come into play. Okay. So the arrows then allow us to generate one and then generate the rest of them from using that. That's where the arrows come into play. So if you go back to the OCN molecule that we had on, was it Monday? Then you could actually put your arrows in and you could move the arrows around to get from A to B to C that we had on Monday. So this, I had on my agenda today to show arrows, how you can start moving the arrows. And so that's kind of what I'm showing here. But this one is, we'll put the thing through that because that's not going to be legitimate. Maggie.
What's the whole thing with like pattern recognition?
I don't know. So one of the things I can say with what I would pattern. I don't understand how they use pattern recognition, that term. Other than there are some things you see over and over again. So somebody had asked yesterday about the sulfur. They gave you 6. See, this is why I don't like to use the because it does strange things. There were 6 resonance structures for the SO4 2- anion. And so the first question they asked was, what would be the formal charges on all of the oxygen atoms and the sulfur? And then they asked about bond order in the resonance hybrid for those 6 resonance structures. And so I guess in my explanation to it, which I'll do again here, is there is kind of a pattern recognition of this in the fact that when you have an oxygen with 3 lone pairs and a single bond, that will always have a -1 formal charge. And if you have a double bond to an oxygen, it will always have a 0 formal charge. So that would be something perhaps you could call pattern recognition. The idea when you see a single bonded oxygen with 3 lone pairs, it's always going to be -1 formal charge. And if it's double bond with 2 lone pairs, it's always going to be 0. The other, I guess, pattern recognition that they were sort of talking about was how you draw resonance structures by moving the arrows. So, for instance, so just so everybody knows, the homework problems that come, there's 2 separate boxes. There's the chapter with the problems in it, and then there's extra homework problems at the end. I have those marked as review. So I don't think it saves your answers. It just lets you go back and do those problems as many times as you need. So there are some trickier problems there. Last year I assigned both sets of problems, and I think people died or came close to it with all the problems they had to do. So I'm making those kind of optional. But one of the problems was a problem that looked like this. They had a double bond to an oxygen, and they had another double bond over here, and then they had like a C triple bond and here with stuff around it. And so what their question was, draw resonance structures for this. How many resonance structures have a carbon with a plus charge? That was their question. And so in terms of the potential, I guess, pattern recognition here is, and it really isn't pattern recognition, it's understanding the fundamentals of how we draw resonance structures and how we move arrows. So it's just kind of, you do a number of problems and you learn this. But in this case, I have a positive charge, and whenever I have a positive charge and I want to write resonance structures, I need to move electrons towards the positive charge. And it's just the opposite if you have a carbon with a negative charge, or you have an oxygen with a negative charge. Then you take the negative charge and you move it away to start the sort of cascade that you end up with the resonance structures. So when you have a positive charge, if I want to write a resonance structure here, I would say, let's pick this pair of electrons up, and now let's move it to the oxygen. So that now the oxygen then will have its 2 lone pairs, so it'll be neutral. And now what happened to the carbon? This carbon right here with a hydrogen on it still has a hydrogen on it, but where's my positive charge go? It's going to have to go on that carbon that was involved in the double bond. So just a couple fundamental things here. If you have a plus charge in one species and you're making another one, it needs a positive charge. You can't just have charges disappear. So if you start +1, all the remaining structures are going to have to be +1. So that means this molecule needed a +1. The question is, who has the formal charge that's +1? It's going to be this carbon, which was this one. Now, why did it become +1? Well, what happened was I picked up these pair of electrons and I gave them to the oxygen. So now the oxygen's happy, it's got its full octet, it's got a 0 formal charge, but what happened to this carbon? It had one of its electrons taken away because it was sharing it with the oxygen, and now the oxygen just basically said, I'm taking both of them. And so that carbon's gets left with a positive charge. Now, if you don't see that, you can always write in your hydrogens and the carbon, and a carbon with, here's more pattern recognition, I guess. A carbon with 3 single bonds is always +1. Is it a completed octet? No. Do we write a lot of carbons with positive charges? Yes, we will. So in this case, this would be a legitimate resonance structure. And then you could say, could I write another one? Well, let's do the same thing. Let's take this pair of electrons and make a double bond and move it over so that we make the double bond to the carbon, so that it looks like this. So that now that carbon has the positive charge. And why did it get a positive charge? Because I picked up the pair of electrons and I moved it over so that the carbon that did have a positive charge now shares, but I did that at the expense of the carbon on the right. And this goes back to some problems or some questions that people had about the half arrows, and then they said you had one arrow that moved towards the positive charge, and then they said, well, you need two arrows if you have a negative charge, because you take the negative charge, which is a pair of electrons, and you move it, but then you got to move something else. That's the reasoning behind that. So they would call this pattern recognition. And to be honest with you, this is something that we will do, sadly, we will do this next semester. So they love to foreshadow in this book. They really like to foreshadow stuff, but foreshadowing to next semester, I found is kind of, I wish that when we got to this next semester, you go, yeah, I remember that in the second week of class. But nobody's going to remember in the second week of class unless we do it over and over and over again in the first semester. So that's why we have to repeat and that's why we have to do that. Okay. Now, this is not the problem that was in the book and that I solved, because what happened is that if the C triple bond N was here, I could continue this process and I could take that pair of electrons and move it there so that then the N would have the positive charge. But in the problem in the book, there was an extra carbon-carbon bond in there. And so the process had to stop because if I moved a pair of electrons, I would end up with 5 bonds to a carbon. But this one, you could end up with another one. Okay. So that's, when you have a positive charge and you're writing resonance structures, you move the electrons towards the positive charge. And then, just to complete this idea, they had another, let's say I have this structure. First, does moving the arrows towards the positive charge, does that kind of make sense? And when you first start, the thing I would do is I would just put in all your hydrogens explicitly, because it'll make it easier to find your formal charges until you get used to this whole idea of drawing these resonance structures. Okay, so let's take this one. That oxygen has what formal charge on it? This oxygen has what kind of formal charge? It has a -1. Why? Because either I calculated the formal charge explicitly, or a single bonded oxygen with 3 lone pairs has a negative charge. Okay, so if I want to draw a resonance structure now with my negative charge, when you have a positive charge, you move towards the positive charge, because remember, arrows mean movement of electrons. So when you have a negative charge, that means you've got a pair of electrons, you have to go in the opposite direction. They have to start the process. So in this case, if I wanted to draw a resonance structure, I would take this pair of electrons, or any of those 3, and I would move it down here to form a CO double bond. Okay. So if I do that, I would have my double bond with my oxygen and my 2 lone pairs. That's what I'm going to draw. But if I move that pair of electrons down to form the CO bond, and I don't do anything else, what am I going to end up with? I'm going to end up with a carbon with 5 bonds. Okay. which, let's see, there's 3, I only have 3. If I get to 10, then I can make a t-shirt out of it. 3 rules of organic chemistry. Number 1, don't take it if you don't have to. Sadly for you, you probably have to take it. That's why you're here. Number 2, no 5 bonds to carbon. Then number 3 is no primary carbocations. We'll get to that later. So no 5 bonds to carbon. So that means I've got to pick this pair of electrons and give it to that carbon. And so if I do that, now that carbon's going to end up with a lone pair. So that the resonance structure going from here to here is going to have my CO double bond with 2 lone pairs on the oxygens and then my lone pair on the carbon. Now, I had a -1 charge to begin with. I still need a -1 in this structure. Where should the -1 charge go? Anytime you have a carbon with 3 bonds and a lone pair, it always has a -1 formal charge. So this kind of shows the way sort of the cascade or the way you move the arrows. If you have a plus charge, you move towards the arrows. If you have a negative charge, the negative charge starts the process and moves then to form the multiple bonds. And normally you have to have a double bond right next to it, so when you bring the pair of electrons down to form the double bond, the other double bond now moves to the carbon.
Is that stable? Like, would it stay, or would it turn into a double bond between that carbon and the one below it?
Okay, good question. Can I continue the process? So in other words, could I take this pair of electrons and form a double bond here? No. Why not? Because then the bottom carbon would have 5 bonds. So the process ends there. So if you're in doubt, move the electrons, but then count up the bonds. If you got carbon with 5 bonds, it can't move any farther. So this is as far as the lone pair will go. And if you don't have those hydrogens, if you just have like the line bond structure without the hydrogens, you're likely to move and form that double bond. So that's that's why my recommendation is that when you're starting out, always put in the hydrogens around the carbons so that way it's easier to see that you're violating the octet rule.
So like the only time in a ring structure that's really possible is the benzene ring then?
Yeah, the benzene ring is a very special case. The benzene ring has 3 double bonds. It has 3 double bonds that are alternating with double, single in a 6-membered ring. And so if I wanted to write the other resonance structure for a benzene ring, what I would do is take this pair of electrons and move it there. But if I do that, I've got to take this pair of electrons and move it here. And then if I do that, I can't stop. I've got to take this pair of electrons and move it there. And so then what happens is that the double bonds basically change their positions. And so these are what are called the Kekulé structures of benzene. And so so we haven't dealt with stability yet. Let's go back and deal with stabilities on these. So these benzene rings are equal stabilities. And August Kekulé, when he came, they knew benzene was C6H6, they just didn't know. This was back in the late 1800s. They didn't know how to structure the C6H6. They just knew that's what its molecular formula was. So they were having a difficult time with that. There were 3 or 4 structures, and you'll see this next semester in the book. They lay them out. I have some old organic books upstairs where they were right in the middle of trying to figure this out in the textbooks, and they said, well, this person proposed this person proposed this, Kekulé's proposed this. It seems like the Kekulé structures are correct. So this is like late 1800s, and indeed he was correct. But he thought of this. The tale is that he was imbibing in adult beverages and fell asleep by the fire and had his dream of snakes, where the snake wrapped around and grabbed its tail. And then he's like, maybe that's what the structure of benzene looks like, and that's how the Kekule structures came into play. And you'll sometimes see the snake being wrapped around and biting its tail. That's an alchemical symbol, which is, there's mysticism and all of that stuff that goes with it, no science. So that's how they came up with that. So those two are equally stable. But remember, the true structure is not any resonance structure, it is the resonance hybrid. And so the hybrid for benzene would have partial bonds all the way around the ring. And those partial bonds, as I've written them, sometimes get shorthand notation as a circle inside the benzene ring. So you may see in lab, when we use benzene rings, you may see a circle, simply because that's what I draw when I draw it. Okay. Now, let's deal with these two. Okay, for those two resonance structures, A and B, which one's the most stable? That's true, we can use our cards, can't we? That's the most democratic way. And I will always put in C that C is the same energy. So for these two resonance structures of having those two, which one would be the most stable, A or B? Or C, that they have the same energy. They're equally stable. All right, let's see what we've got. We've got 21 A's, 11 B's, and 5 C's. Discuss. Discuss for a minute, and then we'll revote. Are you ready to revote? So let's go ahead and revote and see if people change their minds, if we move towards one answer or another. Okay. We move towards answer A, 27 to 8 to 2. Okay, why would A be more stable than B?
Because the negative one should be on the more electronegative.
So we're going all the way to rule 3, that the negative charge should be on the more electronegative atom. And which one is that? Oxygen or carbon? It's oxygen. So indeed, A is the more stable resonance structure for that. Okay. Oh, I love it when this happens. So let's see. If I swipe, nothing happens. I'm back here. Okay. So here's an A and a B, so we'll end up today with this, with the last question here. So these are my two oh, we didn't put formal charges in though. So for A, what are the formal charges for A? Overall has to be a negative charge, so who gets the negative charge? Carbon gets the -1 charge, everything else is 0. Structure B, who has the negative charge? The oxygen, because it's 3 lone pairs in a single bond. Okay, which one's more stable? A, B, or if they're both stable, equal stability, call it C. Okay. So which one's more stable, A or B? Or same stability, C? We have 29 Bs. Okay. So again, same principle. Oxygen versus carbon. Oxygen more negative. Okay, so if you have any questions that we didn't get to today, I don't know if anybody tried to look at a narrated answer key, but I did put up a video on how to do that. The live scribe player is for later videos. If you're having troubles, come and see me or email me. On Monday, we will start the chapter 2.2, which is naming. So bring in as many questions as you need to. There is a video on it, but we can go over that because this is going to be kind of like, I know your head's almost going to explode when you start looking at naming because it's so completely brand new, but that's okay. Try and work through as much as you can, and then we'll work through the remainder on Monday. I did not bring any graded practice problems, so we'll wait until next week for me to give you those. No. It's okay. It'll show up one of these days. I got a bank card. I got a new bank card. I've got my temporary driver's license. I only had a couple, but I'm in the process of trying to figure that out. So, no, as long as I can drive legally now and I can get money out of the ATM, I'm good. I mean,